And hello, everyone. I'm Shengding from Tsinghua University. It's my great honor today to present MiniCPM here. So in today's talk, we will introduce the following contents. The first one is the scalable training strategies, and the second one is the MiniCPM models themselves. And third one is new understandings we get recently about the warm-up stable decay scheduler proposed in the paper. So let's first introduce the learning rate scheduler proposed in the paper, which is the main takeaway from the paper. The cosine scheduler is the most widely used in the large language models pre-training. It has a predefined cycle length T, which is not necessarily equals to the end step of our training S. And it achieves the lowest loss only on the step, only when the step S equals to the cycle length. But it will not be optimal for both S less than T and S larger than T. For example, in the figure, M is the number of model parameters, and 20M means the number of tokens is 20 times of the model parameters. So we can see that when you set the cycle length T to be 20M, it only becomes the best when the token is 20M. And the cosine 40M is only the optimal when the token is 40M. So why does this happen? A guess of us is that when the T is smaller than S, then you get not enough high learning rates. So our guess is that high learning rates will help the model to find a better global optimum faster. And when the T is larger than S, and then we got not enough learning rate decay. So our guess is that the learning rate value will affect the loss value. So decreased learning rate will result in drop in loss. And the training dynamics in learning rate decay process might enable the model to find a better local optimum. So our intuition is that we can separate the two training dynamics and propose the warm-up stable decay scheduler. And we find that there is a significant loss decrease in the decay stage. And no matter when you start to decay, you will all get the loss decrease. And we find that 10% of the decay is enough. So the scheduler keeps a high learning rate in most of the time. There are several advantages of this scheduler. The first one is it has a shared high learning rate stage, which means we can keep training a model without the predefined steps. And when you are eager to deliver the model to the user, you can extract an intermediate checkpoint and decay the learning rate at any time. So when we are keeping training the model with continuously, how low can the loss go? We actually didn't do the experiments of infinite training, and we fit a scaling law of the data horizon. And find that the power law holds perfectly on the data horizon. And we found that when you keep training the model, you will get 3 times compared to 3 times of the model size that we previously thought. And it also benefits the scaling law estimates. When we used to do the scaling law studies, we need to train different models to different number of tokens. So the scaling law is along the two horizon. One is the model horizon, one is data horizon. And now we only need one model for different number of tokens. So in practice, we only train 6 models and extract the checkpoint at D equals 10n, 15n, 20n, 30n, 40n, 60n, and apply 10% decay steps with high quality data. And we measure the finding loss on the training set. And then the fitted loss curve gives us consistent intersection, which means that there is a predictable compute optimal ratio. So as for the compute optimal ratio, it is better than loss because loss is not directly comparable between different model families, but the compute optimal ratio is comparable. For example, the chinchilla optimal, which we use to use it, is 20, which means the data to the model is 20 times. But now in our study, we find that the compute optimal is about 200 times. So we actually need to train on much longer data horizon than we previously thought. It is also supported by the recent trend. For example, the Llama 3 8 billion was trained on 15 trillion tokens. So next, we found that with great loss job comes great responsibility for final performance. The data on the decay stage is much more influential. We do the ablation that we decay with high quality data or the low quality data. And we also add a more fair, fairer comparison that we decay with the low quality data and the SFT with 2 times of the high quality data. And we see that decay with the high quality data produce very high performance improvement. In fact, you can not only just use high quality data in the decay stage, you can select your data with high efficiency using the decay stage. It is an approach adopted by Llama 3 and other data mixing works. And our new paper on MNRP about data selection also leverages the decay stages. Without decay stage on the high quality data, the MMAU score is about just a random choice before SFT. We also conduct other hyperparameter studies, but this is not our main contribution. For example, the batch size prediction is similar to OpenAI method. The basic intuition is that we connect batch size to loss, and we get the optimal batch size defined as the batch size that allow us to use the fewest token to achieve a certain loss. And we also adopt the tensor program from Greg Yang, and it introduced several scaling techniques inside the model, and it introduced several other scaling irrelevant hyperparameters. This allows us to use a very small model, like a 9 million model, and a few data to do Bayesian search on the optimal hyperparameters. And after the techniques, the base learning rate becomes stable in our model. And the final performance is SOTA at the release time. The loss curve is shown in the figure. On the last figure, we also include enlarging batch size as the operation in the middle of training, and finally it produce similar loss decrease, like decreasing the learning rates. So we can also alter the decay stage to produce different models. For example, for the long context model, we start from the last stable stage of WSD. And for the MOE model, we use upcycling start from the last stable stage of WSD. And so why does the loss decrease suddenly when the learning rate decays? Now I'm going to share some of the understandings. We found that we check the parameter change between different checkpoints during training. We found that the parameter change actually becomes smaller in the decay stage. However, despite the parameter change becomes smaller, the update directions of the gradient becomes less disordered. For example, in the left figure, we can left figure shows the cosine value of the gradient's angle between 2 successive steps. We found that in the main part of training that there is both negative or positive values, but when you start to decay, there only contains the positive values. And the loss curvature increases by an order of magnitude, which means it is optimized in a much more sharp loss landscape. So from the perspective of the curvature of the loss landscape, very recently there is a paper from Stanford University that studied that proposed a river valley loss landscape perspective. It refers to the flat dimension as the river dimension and the sharp dimension as the valley dimension. And when you use a large learning rate, it almost optimizes in the river dimension and bouncing around the mountains. And when you decay the learning rate, it starts to switch from the flat dimension to the short dimension, and it feels like to me it is opening in the invisible optimization dimensions. So as a follow-up work, we also study the shape of loss curve, and it depends on the learning rate schedule. We propose multi-power law to predict the loss curve of any learning rate schedule. And based on that, we also optimize the power law, multi-power law, and get a similar form to WSD, but with higher decay ratio and lower ending learning rate. Actually, in practice, the optimized scheduler produce better performance than the empirical WSD. And in summary, the training strategy proposed in this paper has become prevalent. You can use WSD in both Hugging Face transformers and the Megatron LM now. The future directions include deeper understanding of the training dynamics, mix, and design better training strategies. Such kind of studies does not need to really train a large language model, so it is accessible to general researchers. Actually, we want to propose that we can say we are going to study training physics because hopefully you can win the Nobel Prize. Yeah. Thank you for the time, and my poster is in the 6th. Yeah.